So far, you've learned what a battery is, and you've used a battery. So you know that batteries are a device to do a function. They have to perform some kind of work. They run electrical devices. And so as chemists thinking about batteries, we would like to be able to correlate how much work can be done with the particular chemistry underlying that device. We'd like to be able to make a connection between the chemical reaction we're going to put into the battery and how much work we can get out of it. And so we need to be able to link the EMF of a battery or a redox reaction to thermodynamic properties we know from chemistry, like you learned earlier in this course. And that's what we're going to start to do in this particular lesson. We're going to work through in this lesson a connection between the work that a chemical reaction can perform and the Gibbs free energy, one of the most fundamental thermodynamic descriptors of a chemical reaction. So let's get started. In the last lesson, you saw that electrical potential, or EMF, defines the energy that can be released in an electrical process. So let's take a look again at just this definition of what a volt is. The maximum work that an electron going through a circuit can do is given by this equation. The work in joules is just the charge that's passing through the circuit, and the unit for charge is coulombs, times the potential difference that that charge passes through. Potential difference is a voltage, has units of volts, and you remember that by definition, a volt is a joule per coulomb. So the potential difference multiplied by the quantity of charge passing through that potential difference is the maximum amount of work that can be done by that moving charge. And so our goal in the rest of this lesson is to connect up this idea of work, which is associated with a potential difference, to the thermodynamic property that you know already called Gibbs free energy. Now, remember when you first were introduced to thermodynamics in thinking about fuels, you learned that Gibbs free energy is perhaps one of the most useful thermodynamic descriptors that we have in chemistry, because it can be used to determine spontaneity of a reaction. So you know that when Gibbs free energy of a reaction is negative, that reaction happens spontaneously without addition of energy. When Gibbs free energy is positive, that reaction doesn't happen spontaneously. You have to put energy into the system to make the chemical reaction happen. And you also learned that Gibbs free energy defines the heat and work that a particular reaction can produce. So you can trade off heat for work, but Gibbs free energy sets the limit on how much work you can get out of a particular chemical reaction. Delta G defines work. That's important for the next few minutes as we start to think about electrical work. We're now going to think about what Gibbs free energy gives us in the context of redox reactions. Now, in an abstract sense, delta G for a process is defined as the maximal non-expansive work that the system can do at constant temperature and pressure. Let me say that again. Delta G for a process defines precisely the maximum non-expansive work that a system can do at constant temperature and pressure. Now let's step back and think about all those qualifiers I put on that sentence in the context of electrical work. The work we're interested in when we're talking about batteries and redox reactions is electrical work. It's electrons traveling through a circuit. Electrons travel through a circuit at constant temperature and pressure. We can check that off. And electrical work doesn't cause expansion of the system. So it is, by definition, non-expansive work, which means that Gibbs free energy is precisely the measure we need to define the maximal amount of work we can do. So in the context of redox reactions, the Gibbs free energy literally defines the maximum electrical work that a redox reaction can perform. That's powerful. So I'm going to say that again. In the context of redox chemistry, Gibbs free energy defines the maximal electrical work that we can perform with a particular reaction. So what we need to do right now is connect delta G back up to our expression for work that we had at the beginning of this lesson. And that's what I'm going to do right here. Delta G is equivalent to the maximum work that can be performed. We also know that from a physics perspective, the maximum work that can be performed is the product of the charge that goes through the circuit and the potential difference that the charge passes through. So delta G is absolutely equivalent to the product of the charge that goes through the circuit and the potential difference that that charge falls through. So in the last lesson, we were calculating how much energy is released by a charge passing through a particular voltage. You now see that maximum is the amount of work that an electrical circuit can do, and it's also exactly delta G of whatever redox process is driving that particular chemical reaction. Now, we write chemical equations in terms of single electrons or single reactants, but of course, on the scale of actually doing something, it's much more useful to think of chemistry in terms of moles. So we're going to start to write our equations taking into account this idea of a mole to be on the right scale for the things we're actually going to make. In order to do that, electrochemists have invented a new constant. That constant is the product of the charge of an electron with Avogadro's number. So it's basically the charge of a mole of electrons. And it works out to 96,485 coulombs per mole. So 96,485 coulombs is the amount of charge in a mole of electrons. This constant, again, is called Faraday's constant, and we usually abbreviate it when we're writing equations with the abbreviation capital F. Don't confuse that with force. In electrochemistry, it stands not for force, but for Faraday's constant, the charge in coulombs of a mole of electrons. So suppose that n moles of electrons pass through a circuit. How do we define the work that that circuit can do, the maximal work of the circuit? Again, maximal work is defined by delta G for the chemical reaction driving the work. Maximum work is just abbreviated with this little w. But now we can substitute where we before had charge. We can use Faraday's constant times however many moles of electrons are moving through the circuit. And again, we have the potential difference. Notice that I snuck in a negative sign into this equation. That's because Faraday's constant doesn't show us the sign of the charge of the mole of electrons. Alternatively, you can think of this thermodynamically as being a situation in which the system does work on the surroundings. So by definition, that work is negative. Okay, when we start tying this up to particular chemical reactions, you have to remember that N, that little n, corresponds to the number of moles of electrons that are transferred in the chemical reaction. So this is why in the last series of lessons I made you learn how to balance redox reactions, because you have to know how many electrons are transferred in the balanced redox process to be able to calculate how much work you can do with that redox process. So now the only thing that's left to do is to remember that in the last lesson I showed you that potential differences can be abbreviated with the symbol capital E. So the Gibbs free energy is equal to the maximum non-expansive electrical work is equal to minus NFE. So the potential is directly connected to the Gibbs free energy of the underlying chemical reaction. This is a key equation in the thermodynamics of redox reactions or electrochemistry. It comes up over and over again because it allows us to connect Gibbs free energy, a really central player in chemical thermodynamics, to electrical potential, a central player in the physics of understanding circuits. So this is very powerful. You're going to want to understand where it came from. You're going to want to understand how to use it. You might even want to be able to derive it. You'll certainly want to know it. So let's solve a few problems using this newfound knowledge. If a cell potential E is positive, will the corresponding redox reaction be spontaneous? So let's look back at our equation now. Delta G equals minus NF E0. N and F are both positive values. And I've just told you that E is also positive. So the product of three positive things is positive, and then there's a negative sign in front. So delta G will be negative according to this equation. What did you learn in thermodynamics? When delta G is negative, is the reaction spontaneous or not spontaneous? When delta G is negative, the underlying chemical reaction is always spontaneous. So what you've learned in this particular problem is that for a positive potential difference, the underlying chemistry is negative in terms of Gibbs free energy. It's spontaneous. So a chemical reaction with a positive potential difference will occur spontaneously. That's key. We're going to use that over and over and over again in the next several lessons. Let's look at this second problem. The Gibbs free energy of a redox reaction is 110 kilojoules for a reaction involving the transfer of 2 electrons. What is E cell for the electrochemical cell created using this reaction? Is the reaction spontaneous, and could it be used for constructing a battery? So we have delta G equals minus NF E. So our goal is to determine the potential for the cell. So we want to rearrange this equation to solve for E. So E equals minus delta G divided by NF. This is just some arithmetic. I multiplied by -1 on both sides to get the -1 over there, and then divided by N over F. So that means we just need to put in some numbers now. Minus 110 kilojoules is our minus delta G, divided by how many electrons are transferred in the process? 2 electrons, times Faraday's constant, which is 96,485. What units does Faraday's constant come with? Coulombs per mole of electrons. This is 2 moles of electrons in the balanced chemical equation. Those units now cancel. So what do we have? We have negative 0.12357, oops, that's a 7, kilojoules per coulomb, which is just 0.57 joules per coulomb. And you'll remember by definition, a joule per coulomb is a volt. So our answer, oops, I almost lost a negative sign there. Our answer is just negative 0.57 volts. Do you ever buy a battery with a negative voltage written on the side of it? Absolutely not. And so we immediately recognize this is not spontaneous. Cannot power battery. Just like in the last lesson, we talked about water running from high potential to low potential. Electrons also run from high potential to low potential. If you have a potential difference which is negative, that's pushing electrons uphill. That's not spontaneous. And that makes sense because our delta G in this particular problem was positive, which we know from our thermodynamics means the reaction is not spontaneous. Let's look at one more problem. The reaction in a fully charged battery with a 2-electron redox reaction generates a cell potential of 1.25 volts. What is the reaction Gibbs free energy? This is the simple equation the way we wrote it initially. Delta G equals minus NF E0. So minus 2 moles of electrons times 96,485 coulombs per mole of electrons times 1.25 joules per coulomb. Coulombs cancel, moles of electrons cancel. We'll get an answer in joules. That answer turns out to be minus 241 kilojoules. So you can see we can go directly from a potential difference to a free energy. This relationship, this connection between potential and free energy is one of the most central in understanding redox chemistry. So use it to solve a few problems before you go on to the next lesson. Make sure you understand it. Make sure you're understanding potential as a driving force. Make sure you're understanding that Gibbs free energy defines the maximum work that a system can perform.